Hi, everybody. We are going to take a look today at confidence intervals applied to OLS regression coefficients. We'll also take a quick look at generating coefficient plots, all with some examples in Stata. So let's take a look. All right, so this is a follow-up to our hypothesis testing part 1, link in the description. That walks through your basic t-statistic applied to OLS regression coefficients. Right? So now we want to expand that out, looking at the confidence intervals that can be really useful ways of thinking about the accuracy of our point estimates, those beta hats that we generate. Okay? So in terms of our definition, our interpretation, a confidence interval, and we'll stick with a 95% confidence interval. Obviously, that number can change, and your calculation will depend along with that choice. But a good way to think about it is it shows the interval, the range in which 95% of our sample estimates of our parameter, of our OLS beta, will lie, right? So this again goes back to that theoretical idea of repeated sampling, right? If we could randomly sample from a population over and over again and estimate our model again and again and again, what this interval tells us is that 95% of the time, the coefficient of interest will lie within this range. Okay? So obviously the wider that range is, the less precise, the less accurate our estimation procedure is. Okay? And again, so when we talk about an OLS regression model, we are making the naive assumption here that we're in that Gauss-Markov world, right? So imagine we have a multiple regression model, y as a function of x1 and x2 in that linear combination of our coefficients. We're making our kind of basic assumptions that that error term, that ui, is non-autocorrelated, it's homoscedastic, it has a constant error variance, it is uncorrelated with our x variable, so all of our x variables are exogenous. And crucially, for the process of hypothesis testing, we make the normality assumption as well. Okay, so under those conditions, with an assumed, or at least asymptotically normal distribution for that error term, we can calculate the probability of being within a given range of outputs if we know that distribution, right? So the distance from the center of a normal or a t distribution can be calculated, right, in terms of the percentage probability of lying within that range. So we're talking about the area under that t distribution, or that normal distribution bell curve. Okay? So this sounds a lot like what we did with our hypothesis testing, right? We wanted to have a given percentage, right, significance or confidence that the true value is beyond a certain point, past a critical value, right? And definitely the issues are related. One key difference here is that with our t-statistic hypothesis testing, right, the assumption there was, right, under the null hypothesis, that the distribution was centered at 0, and we were looking for evidence to counter that, right, to reject that null hypothesis. When we make these confidence intervals, we're implicitly assuming that the distribution is centered on our estimated value, right, on the beta hat itself. And that lets us calculate those percentage areas, right, around that estimated value. So there's a little bit of a different point of view here versus that t-test. And in terms of what we can do with the information that comes out of this, again, why is this going to be useful? Well, partially it's going to mirror the hypothesis testing results, right? So if 0 does not lie within that interval, that's consistent with saying we are 95% sure, right? 95% of the time, our estimated value will not be 0. That'll be consistent with a statistically significant coefficient estimate. And the other way to think about it, right? The more precise our estimate is, the more accurate it is, the smaller that interval is going to be. So we got the idea here. Let's call up some numbers and then kind of see exactly where these values are calculated. Okay, so we'll use the same kind of practice data set that we did in hypothesis testing part 1, right? So we're going to call up that CEO salary data set. I keep typing that wrong. So it's CEO sal 1 with the BCUs command. So again, this comes out of the Wooldridge Introductory Econometrics textbook. And let's go ahead and start with the same regression that we ran last time. So we're going to regress the salary of a sample of CEOs as a function of firm level sales, return on equity, return on sales, and then we'll throw in a dummy variable for whether or not the firm is a utility or not. Right. So let's take a look at our top row here. So we've got all the information for our sales variable, so our coefficient, its standard error, its t-statistic, its p-value, we'll get into that next, and its confidence interval, right? So based on our definition here, what we can say is if we reran this sample, right, again and again and again, 95% of the time, we will expect our estimated coefficient to lie between negative 0.005 and positive 0.03. That's kind of the range of expected values. Okay? So, how were those numbers calculated? Where did they come from? Well, again, the assumption here is that we are centering our distribution on the coefficient estimate itself. So from our example, it would be the 0.012. And a good way to think about this is that we are using that same t distribution, right? So the ratio of the coefficient to its standard error, and then figuring out how much, right? Or I should say, we're trying to figure out in what range, in what interval will we find 95% area, right, about that estimated coefficient. So if we go ahead and divide the coefficient by the standard error, we can just add and subtract the 2.5% significance critical value, right, from that center point. And that'll give us 2.5% area in the left-hand tail, 2.5% in the right-hand tail, and 95% in the middle. Okay? And in fact, there's absolutely nothing wrong with doing it that way. And all you need to be able to do is look up the appropriate t critical value in the table, and we'll find where that 95% is going to lie. Okay? So our calculation here would be our t-statistic for the coefficient, the beta hat over its standard error, plus or minus the 2.5% critical value. And like we said, that's absolutely fantastic, except it would be a lot more useful if these ranges were in units of the coefficient itself, the beta hat, rather than the beta hat divided by its standard error. So that's simple enough, right? If we take that beta hat over standard error plus or minus the critical value, multiply through by the standard error, and now we'll get our confidence interval, the same result where 95%, where we have 95% confidence that our values will lie, but it's in units now of the coefficient itself. So we don't have to do any mental gymnastics to interpret what the numbers actually mean. So our plot now becomes centered on B1 hat, right? And the upper and lower bounds are again in units of our coefficient. But the areas of concern are still exactly the same. So these numbers that we see here for our sales, the negative 0.005, positive 0.03, this is how they are calculated. Okay. So to actually walk through the the exact process. The only thing that's missing is the appropriate critical value, right? So again, we flip to the back of the book, our statistics book, our econometrics book, and we look at the table. And of course, the critical value depends not just on the significance, but also on the degrees of freedom, our n minus k minus 1. So as we saw last time, we're not going to have an exact row in our critical table in most cases, right? So here we have 209 observations. We have 4 explanatory variables, so k of 4, and then minus 1 more for the constant. We have an n minus k minus 1 of 204, which again doesn't have an exact row to give us our critical value. So we're somewhere in between these ranges here for our 2.5% one-sided or 5% two-sided. So we're going to use the inverse t-tail command in Stata to calculate the exact critical value appropriate for our degrees of freedom. So we can generate a new variable, call it crit5, call it whatever you want, but that seems to make sense. And the command here within the generate statement is invt tail, and then we put in our degrees of freedom, in our case 204, and then the area that we want in each tail of the distribution. In this case, it's the 0.025. Hit enter. We've got a new variable created here, and again, it's creating this for every observation, so we'll just take the average of it. So summarize our variable crit5, and we get a value 1.97, which should lie right in between these guys, and it looks like it does. And that's the last kind of missing ingredient for doing this calculation. And if we wanted to walk through it, for that sales variable, right, the beta hat plus or minus our critical t times the standard error, our coefficient, the 0.01261 from here, plus critical t at 2.5% times the standard error, gives us the upper bound of our confidence interval here of the 0.03, and then the lower limit coefficient minus critical value times the standard error equals minus 0.0051. So again, what does that tell us? 95% confidence that our outcome will lie within that range. Note that 0 is within that confidence interval, so that's consistent with an inability to reject the null of 0 or an insignificant coefficient. So this t-stat will not surpass the 5% critical value. Okay. And we should be able to do this same calculation, and the critical t is going to be exactly the same for all of our coefficients, and replicate where these values come from. And the picture would look something like this. So again, it's centered on our beta hat coefficient, the lower bound and the upper bound. We've got the middle 95% here. And that's the range, that's the realm that we expect our values to fall. Okay, last little thing here is just to get the visual of this process, right, by plotting our coefficients along with their 95% confidence intervals, right? So a really nice, useful way to give the reader of your regression results of your economic research, tell a little story about how the levels of your coefficients and their accuracy, their 95% confidence intervals, changes across specifications and across variables. And luckily, Stata has a command that's going to create this for us in a real easy way, the coefplot command. Right? So if we just, first off, we need to install this, right? So we need to do ssc install coefplot, coefplot, and that's going to install. So now we're ready to use it, and there's a whole documentation as with most commands. So if you type help coefplot, you'll get a lot of different options, much more than we'll talk about here, but that shouldn't have any trouble with that. And if we just type this in without any options, coefplot. So what that's going to do is give us the plot of the coefficients in 95% confidence intervals for the most recently estimated set of results. So it's going to come back to this regression that we have up here. And let's see what we get. Not great, right? So what this tells us is these are the values of the coefficients, the dots, right, for our various variables whose labels we actually can't read. And then these bands here are the ranges of the confidence interval. And you can see right away the problem of using this default plot is that there's only one unit of measurement, right? And our coefficient values are going to be much different depending on the units of measurement of our variables. And so you can't even see the 95% confidence intervals for these top coefficients relative to what we have down here. So we're going to make some adjustments here. Before you do anything else, probably the first adjustment I would recommend is we would go coefplot, and then we want to drop the constant. So go drop underscore CONS, and then maybe put a line at 0, so x line 0. So that'll help a little bit. All right. So here is 0. Here's our coefficients. We got rid of the constant, but we still have this one variable that is dominating the units of measurement here, and we still can't see exactly what the variables are. So one other kind of option that I generally always use here, so we bring that back up, drop the constant, put an x line at 0, and let's use the no label option. So no labels. So that'll give us the names of the variables. So that looks a little bit better because it was trying to fit the entire text of the label of the variable in there. So sales ROE RS utility, and again, the magnitude of that utility variable is dominating what we see here. So here is kind of the most useful application of this command is to show multiple specifications, right? So let's kind of go back to the beginning and run a regression of salary just as a function of sales. So again, normally you wouldn't want to run a regression with only one variable, but let's go ahead and do that, and then let's store those coefficients, so EST, STO, so estimate store, and let's call it model 1. And then we change the specification. We run the same regression, regress salary as a function of sales, but now we add in ROE. You see where this is going. Now let's save this EST, STO as model 2. And just for the sake of the example, let's do it one more time. Regress salary as a function of sales, ROE, and let's put that utility variable in there. And let's save this EST, STO, save these coefficient estimates as M3, model 3. Now what we can do is use that coefplot again and apply it to model 1, model 2, model 3, so the names that we applied to those estimates. But now, instead of dropping the constant, let's just keep one variable, sales. And let's also put in the line at 0 for reference, and let's also do the no labels option. So just put in the name of the variable. And what this should show us is how our coefficient estimate changes across specifications. So this would be something we would call a robustness check, right? No matter what we do to our model, we always get these similar results, right? So we get a positive coefficient estimate in each case, but note that in each case, that confidence interval, right, includes 0. So in none of these specifications do we have a significant coefficient, but we can just look at this plot and it tells us exactly the story of our kind of model specification search, right? As it changes, how do the results change? So maybe not the greatest example, but you can see how this would be a really useful tool. So hopefully this was helpful. We will take a look in hypothesis testing part 3 at the p-value, the probabilities. And so I will see you then. Thanks.